Good morning. Today we're here to have Phil talk with us about his next new project. Before we start the program, can I ask everyone to turn off their cell phones, please? Or turn them on mute so that there's no disruptions during today's talk. Thank you very much, and let's give Phil a great big round of applause. Well, okay, I guess I'll... how many people here don't know what my new project is? All right, so there's... and how many people do know what it is? Okay, so that's... I'm glad you do. Well, it's Secure VoIP. 9 years ago, I did PGP phone. And at that time, the internet wasn't ready for it. No one had broadband. SIP did not exist as a protocol. RTP was just barely getting started. And I had to devise my own protocols to do internet telephony. And so I just created PGP phone with improvised protocols. But over the years, PGP phone became a sort of an orphan product, and it hasn't been supported in all those years. Now the internet is ready for it. Now, lots of people have broadband. There are some nice protocols for supporting voice over IP, and the whole VoIP industry is now being built on those protocols. So what I've got now is a secure VoIP client that is much like PGP phone, but brought up to date with all the modern VoIP protocols. Except for the crypto. The crypto is still my own. It's not like the crypto that's been talked about for VoIP. Now, I don't think I should have to make the case too much to this particular audience as to why you need secure VoIP. You guys are in the business of understanding the dangers of, the vulnerabilities of the internet. So you already know that as we move our phone calls from the relative safety of the public switch telephone network, I say relative safety, I know that there's vulnerabilities there too, but compared to the internet, it is relative safety. The internet compares to the public switch telephone network sort of like it's like comparing the well-manicured neighborhood of the PSTN to a sort of a crime-ridden slum of the internet. On my server at home, I can see on the console every day just scrolling by these break-in attempts, and hopefully they're all being repelled, but just the fact that those things are going on all the time is an indication of what is going to be happening to our VoIP phone calls as we move from PSTN to the internet. To not protect them seems a bad idea. People kind of stumbled into email without thinking about protecting it many years ago, and I saw a need to protect it, and that's where PGP came from. And now today there's certainly a lot better awareness of why email has to be protected. But people are not as aware of protecting their phone calls, I think, because they've enjoyed the relative safety for 100 years now of making phone calls on the public switch telephone network. But I think that the average user who has enjoyed that safety is going to get a rude awakening when they discover how bad things can be on the internet. So I looked around a little bit at the protocols that are currently being considered for encrypting VoIP phone calls, and I didn't feel that they were the right protocols. For a long time, there have been secure phones available for the PSTN. Back in 1991 or 92, AT&T came out with the AT&T 3600, which was something that used a DES chip to encrypt phone calls. And in fact, it sort of pushed the government, it sort of alarmed the NSA and the FBI, especially the FBI, that they needed to come out with the Clipper chip. And it was one of the precipitating influences that caused the Clipper chip to be proposed in 1992. Now, we all know that the public didn't embrace the Clipper chip with much enthusiasm, and fortunately, it was politically defeated. But the AT&T 3600 did not rely on a public key infrastructure. It simply did a Diffie-Hellman exchange between the two parties and displayed a hash of the shared secret, and that hash could be read aloud by the two parties from their LCD displays and compared to see if they were the same. If they were the same, that would mean that there was no man in the middle. I think that's a pretty good scheme, and Eric Blossom did the same thing a few years later with his phone. I can't remember what the phone was called. Do you remember, John? Yeah, just his secure phone. It was a very nice product. It did the same kind of thing, did a Diffie-Hellman exchange, 2000-bit Diffie-Hellman in triple DES running in counter mode for the voice encryption, and the users would read aloud some hex digits and compare them. But now, and the beauty of both the AT&T 3600 and Eric Blossom's phone is that at the end of the phone call, when you hang up the call, the keys are erased. Now, the AT&T 3600 suffered from using 56-bit DES as the block cipher, and so we all know that the DES is vulnerable because its key is too small. But still, the overall design of it was a good design, and Eric's design was also a good design. And so I thought, and when I designed the PGP phone, I did that at about the same time that Eric was working on his, and I took the same approach. Did not use an external, centrally managed public key infrastructure. I didn't want to use certificates. I didn't want to use any persistent key material because I wanted to have the phone erase its keys at the end of the call so that no one could retroactively reconstruct the plain text of the call by capturing the phone and sucking the bits out of it after the call. And so I think any good secure phone should have that property. And of course, PGP phone did, and so does my current project. But some of the VoIP protocols that are currently being considered do rely on a public key infrastructure, and sometimes they even rely on one of the proposals being currently considered is to send an S-MIME encrypt, sort of like an email message. S-MIME is an encryption standard for email, and one of the proposals that is currently under consideration in an IETF RFC is to take a session key for the phone call, encrypt it using the S-MIME format. It's kind of like using PGP, you know, it's an email encryption format, and sticking that into the SIP packet and essentially emailing it to the other party. And this means that if later on you could obtain that key from the, you know, it's a persistent key. It's not erased. It's something that could be captured and decrypted. If you could obtain the private key of either party. So I just thought that was just the wrong way to do it. There has been some discussion of using self-signed certificates without relying on a certificate authority. But even there, you have to worry about a man-in-the-middle attack, because if they're self-signed, then how do you know that they're really the key of the other party? And sometimes the remedy to that involves getting it from a trusted server. And again, we're back to the point of relying on a third party to help us make an encrypted call between two consenting adults. It seems to me that two people ought to be able to talk to each other without relying on trusting a third party. And so that's the approach that I take here. I'm going to do a little demo here. and I hope it will work. It should work, right? All right, that's good. Now I have, let's see if this works here.
Fort Meade.
Fort Meade. You're not actually Fort Meade, are you?
No, not actually, no.
This is Stephen Rossi. He's in the down the hall in another room. So what we've got here, Steve, you can hear me, right?
I can, yes.
Okay. What we've got here is I'm going to read aloud these digits here. U9W.
3DQ.
3DQ, he says. And they in fact, are as predicted. This means there's no man-in-the-middle attack. Now, in a real product, this is a prototype. In a real product, these buttons wouldn't appear. There's no need to have a Go Clear or Go Secure button because it would just go secure at the beginning of the call and stay secure for the whole call. But just to give you an idea of what this means on the wire, you guys are all engineers, so this shouldn't impress you that much, but this goes really well in a demo to a non-technical person. If I just click on this, read what it says here. So that's what ciphertext sounds like. Let them eat ciphertext. Let me do that again. I just love that. So that's what the wiretapper hears. You know, I just took the ciphertext packets and just played them right through the codec, and that's what it sounds like. Yeah. Yes, but you don't necessarily have to recognize the voice of the person you're talking to. You could be calling someone for the very first time and you have no idea what their voice sounds like. But if the voice that reads these digits matches the voice in the rest of the conversation, then there's no man in the middle. Because, you know, the idea is you want to know if you're talking to that person and not a man in the middle. What this is a hash of the shared secret from the Diffie-Hellman exchange. If the person at the other end, the person that you think you're talking to, reads this aloud in their voice, and you're matching it against the voice in the rest of the conversation, if that matches what you see here, then that's not the voice of the man in the middle. The man in the middle doesn't have the same voice as the rest of the conversation. Now, you could be talking to the man in the middle the whole time, but who cares about that? I mean, you know, so what? That's kind of a trivial attack, you know. How do you know when you call anyone now that you're not talking to an impersonator? You know? I mean, you're supposed to use your common sense about that. You don't look at the world through a radar screen. You don't, you know, how do you know your mom's not a Martian? You have to use your common sense. And what? Well, yeah, I guess that's possible, but I mean, that's not really a part of a plausible threat model. You got to look at this from the point of view of the attacker. I mean, suppose it's a powerful intelligence agency. Okay? I mean, they want to passively listen to the call. You know, they don't want to get caught. They don't want you to discover that they're wiretapping. So they're not going to take a chance and get in there and have a guy that talks simultaneously like a UN translator in real time, you know? I mean, what if he screws up, you know? that's not part of a plausible threat model. And you can't protect against all threat models. Look, I mean, you might have a threat model that involves the attacker inserting hostile software into your computer. That's why I use a Macintosh instead of Windows. You can't protect against every threat model. I mean, that's sort of beyond the scope of this product.
Phil?
Now, if they were actually repeating the entire conversation, if they were like doing that, yes, then they could make a match. But what I was talking about, if the voice doesn't match, it means that he substitutes, the man in the middle substitutes his own voice to recite the wrong digits, the digits that do match, and then gets out of the conversation and allows you to talk to the other person.
Yeah, what you know from those digits is that the person who's talking to you actually picked up the other end of the phone. You don't know that you made the right phone call even, but you know that there is nobody in the middle that is in it. So you know that the end-to-end connection is secure. You don't know anything about the ends.
You have to worry. I mean, if you're worried about really, there's all kinds of threat models that could compromise your security. I mean, look, what if Monica Lewinsky had used one of these to talk to her best friend, Linda Tripp, and nobody could wiretap it in between? You think that would have protected her secrets? No, because you can't, because Linda Tripp was a rat. And you don't know if things are secure at the other end. Maybe the person is going to reveal the secret information at the other end. What we're trying to do is we're trying to prevent a wiretap in the middle. And we want to prevent the classic man-in-the-middle attack, which is an attack on Diffie-Hellman. And in fact, you can even think of that attack in non-mathematical terms. Imagine, for those of you who aren't familiar with the mathematics of Diffie-Hellman, you don't actually have to be familiar with that. Imagine that you bought a VoIP phone at Walmart, and you have one on your desk, and it's secure. It's a secure VoIP phone, and the other person you want to talk to also has one. The man in the middle goes to Walmart and he buys two of these things, two of these secure phones, and he brings them home and he plugs them in, and he's got one of them connected to you and the other one connected to your friend, to Alice and Bob, okay? And so when Alice and Bob call each other, Alice talks to the man in the middle, and the man in the middle talks to Bob. And he's got these two phones. He takes the two phones and he holds them up so that the earpiece and the mouthpieces line up, and the sound can go through the air gap, and then the eavesdropper can listen in. The eavesdropper doesn't have to know about the mathematics of public key cryptography or the Diffie-Hellman algorithm. This can be done just by buying Walmart phones. But if that's the case, the session keys will not be the same between this link here and this link here. And to discover if they are the same, we read these digits aloud, and if they're the same on both sides, it means there's no man in the middle. Well, what I do is I do Diffie-Hellman with hash commitment, so that only 3 characters have to be displayed. I send you to briefly put the algorithm. I'm publishing a document that describes in great detail this protocol. But what I do is I compute my g to the x for Diffie-Hellman. I compute a hash of that, send the hash to you, and then you reveal your Diffie-Hellman component to me. And after I see your Diffie-Hellman component g to the x come back to me, I then send you my real g to the x, because I've already sent you the hash. You then hash it and compare it with the hash. And then if they match, you proceed with the rest of the Diffie-Hellman calculation. At the end of the process, it means that we're left with a shared secret that we only have to display 3 characters of it. The man in the middle would have to, if there's 3 characters, let's say they were 3, let's suppose these were 3 decimal digits instead of letters, because I don't want to have to do the math. If they were 3 decimal digits, then he would only have 1 chance in 1,000 of fooling you. And so that's a good position to put him in. He's not going to be confident enough to proceed. In fact, there's really 6 digits here, so that'd be 1 in a million chance of fooling you. He's not going to proceed with the attack if he thinks that he has only 1 chance in a million of success. So, hey, Stephen, are you still there?
Oh, yeah.
What?
Yeah, I'm here.
Yeah, okay, good. So this actually works. Glad to hear that. Hey, I'm going to show you something here. You see this Go Clear button? Suppose you want to go switch back to plain text. Stephen, when I press Go Clear, you should press Go Clear too. I don't know if I showed you that feature. Did I? Yeah, I did show you that feature. Okay, here you go. Okay, now he's pressed his Go Clear button. Why did I make him press it too? Well, because what if he was telling me some secret stuff and I pressed the Go Clear button? We certainly wouldn't want him to keep talking about the secret stuff when we're not secure, right? So by making him press it too, that puts him on notice that he better clam up about the secret stuff. Now, I'm going to press Go Secure again, and here we go. That little bong sound, by the way, I got from Eric Blossom. I had some of his phones for a number of years, and I used them quite a bit and really liked the sound that it made when it went secure. And I asked him to send me a WAV file, and he sent it to me. So now I've stolen his WAV file, or he gave it to me. So it makes now the same sound that his did. So it did a new Diffie-Hellman connection. Now, in between when we were not secure, hey, Stephen, press your Go Clear button, please. Okay, now I press mine. Okay, now, Stephen, can you hear me?
Yes, I can.
Okay, now we're making a normal SIP phone call. This is a plain text call. And, well, I can't really, if I click here, nothing happens, because this is really just the packets. They're not encrypted. Why don't you press your Go Secure button, please, Steve? Okay, we're secure again. And now you see that these digits have changed because it's a different session. WXQ.
SHJ.
Right. All right. Of course, you don't always have to read them aloud. It's just if you're feeling paranoid. If you skip it, then that gives an opportunity for the man in the middle to attack. But we're banking on the fact that he can't assume that you're going to be lazy. His fear that you might read them aloud is what keeps him away. So, there's other aspects to this protocol too. I do some things here that have not been done in previous secure phones. There's kind of a persistence of key material that SSH uses. If you SSH somewhere and there's kind of a baby duck mechanism where you exchange some information that there's a continuity of keys in every subsequent session. The man in the middle has to be present in the very first SSH session, and if he's not present then, he can't get in later. The same thing is true here. You notice here at the bottom it says call connected secure since this date and time. That means that we made our first call at that date and time, and each time we make a call it does another Diffie-Hellman exchange. However, it mixes in a shared secret from the previous call in with the new call. And that way, it means that not only is there no man in the middle in this call, what if we didn't read these digits aloud? What if we made 100 phone calls between ourselves over the course of 1 year? Well, and let's say we just never read these digits the whole time. We were just incredibly lazy and just didn't read them. Well, after 50 phone calls, what if I just decided that, I should read those digits? So I read them, and they match. They're what they're supposed to be. Not only does that prove that there's no man in the middle for that particular phone call number 50, it also retroactively proves that there never was a man in the middle all the way back to the first call 6 months ago. That's something that other secure phones don't do. That's really good for peace of mind. It means that people can be sloppy when they feel like it and diligent when they want to be diligent. And if they have a moment of diligence, in a lifetime of sloppiness, that moment of diligence protects them even during their lifetime of sloppiness. Between the same two people, yeah. Yeah, if there's a man in the middle from the very beginning, he's sort of a prisoner. He can't ever leave. And the first time you discover him, yes, you can clear that. But if he is in the middle the first time, and he puts these up here, and you just never checked them, you just never read them aloud, then if he hangs around and listens to a bunch of the calls and he decides he's getting bored and wants to leave, well, if he leaves, you're going to discover it, because at the moment that he leaves, it's going to produce a discontinuity in this continuity of shared secrets. So it's really very inconvenient for the attacker. Anyway, as you can see, or at least I hope you can see, you don't need a public key infrastructure for this. I think we're done here. I'm going to hang up. See you later, Steve. You might hang out. I might call you again.
All right.
So, anyway. So this is a VoIP client that's actually based on an open source VoIP client. I just added crypto to it. That's something I couldn't do back in 1995 because, 96, because at that time there wasn't any other, there were no standards. But now there are standards, so I just found an open source VoIP client and added crypto to it. Now I can call any SIP phone in the world. And of course it won't be an encrypted call unless I'm calling one of my own. But you can still interoperate with the rest of the SIP universe. And that registers with Free World Dial-Up. So we're using a SIP server at Free World Dial-Up. The block cipher used is AES running in counter mode. I'm actually running the SRTP protocol, a protocol which resembles very much the protocol I used in PGP phone in 1995. That's for the packet encryption. And then, of course, there's a Diffie-Hellman exchange at the beginning. So I'd like to open it up for questions. There were a couple of questions, but you can have more. Yeah?
The ciphertext of the call itself, are there technical differences between the presence or absence of voice signal?
No. No. I mean, I suppose actually, what I'm doing is I'm crypting all the packets. Now, you might have a codec that slows down. There's a lot of codecs in the VoIP world. I don't know which one you might be using, There may be some codecs that slow down what they send if there's silence. And other codecs that don't slow down. They just keep sending them in at full bore. So you might have the ability to tell something from that. But that's something that the codecs are doing. And if you don't like that, then don't use those codecs. Yeah? Yes, I have a product roadmap with a number of products, and one of them is a server in your office that turns all the VoIP phones in your office into secure phones. Not really. They're not secure for the first 10 meters, but they're secure out to the cloud. Yeah. What? Yes, you can reset those. Yeah? Oh, okay. Wait, he had his hand up first. Yeah? What kind of reaction from the government? I think that this is something that we went through in the 1990s with PGP and with other encryption products, we had a debate that had the participation. We had a debate about, is the world better off with strong crypto, that went on through the 1990s. And that debate went on for several years, and it had the participation of Congress, the courts, journalists, academics, cryptographers, the NSA, the FBI, the White House. Did I mention Congress? Yes. Advocacy groups such as EFF and EPIC. People from all sides were arguing about it. And over the course of the 1990s, and it went on for several years, as most of you know, we ultimately decided as a society, collectively, that we're better off with strong crypto. And the export controls were lifted in the United States in 2000. The same debate was going on in Europe. The French lifted their domestic controls on cryptography. The British backed away from some of their stuff that they were doing domestically on cryptography. And the rest of the European countries who had been considering controls on cryptography had dropped those plans. And so most of the Western democracies went along with the same collective decision. I think it was a good decision. It was a decision that we all took time to make. We all heard from everybody. And it wasn't perfect consensus. The FBI hung on to their position all the way to the bitter end. But the rest of the government pretty much went along with the collective decision. And so I think that, right now with this product, it's really the same issue. But I think we've been through it already. We did not see a clampdown on crypto after 9/11. And I think the reason why is because of the thoroughness of that debate in the 1990s. A centerpiece of that debate was what happens if terrorists use this technology. That was not something we're going to smack our foreheads after 9/11 and say, oh my goodness, we didn't think the terrorists would use crypto. Oh, now we better put some crypto controls in. No, au contraire. The central theme of that debate was what happens if terrorists use crypto, versus the rest of society benefiting from crypto, And so I don't think that much has changed. Yeah.
I'll just add in, too, that one of the things that I believe was a factor in this was that whatever else you might think about Mr. Ashcroft, he was one of the sponsors of the SAFE Act, which was the Security and Freedom Through Encryption. It was one of the bills that never made it through Congress to liberalize the export laws in the crypto wars. So, while we might have disagreed with him on some things, on the free use of crypto, he was on our side, and that was one of the key factors that I believe counted with the fact that 9/11 really had no effect on crypto laws.
Yeah. Well, when do I anticipate this being available? Well, this thing actually works. It's good, strong crypto. There's a few bugs in the VoIP client. I'd kind of like to have a better VoIP client. Anybody out there who's, by the way, this is developed in Python, oddly enough. The open source VoIP client that I started with is written in Python. It's called Stum. And it was supposed to be multi-platform, but I haven't noticed. I've noticed that all the platforms are not supported equally. Mine runs on a Mac. My prototype is pretty much a Mac-only prototype. A real product would, of course, have to target the PC running Windows first. That's clearly commercially where you want to be. This is not really the product. This is a prototype. The real product, I think, will be written in C, or one of the C variants. And we still can do some more development on this. If people want to volunteer to go work on the Stum VoIP client and make it better and get the bugs out of it, that'll make this better, because this is really just kind of a plug-in for that. Yeah? Right. No, because there's a random number generated for the cryptographic ID, and it's going to be different for the two of them. Now, something I didn't elaborate on during this is that in order to take advantage of the retained shared secret from earlier calls that gets mixed in with the fresh shared secret from the new Diffie-Hellman calculation, you need to use an address book so that you know that you're talking to the same person from the earlier calls. And I didn't show that here, but that's an important part of the security. And if you don't have an address book in your VoIP client, that's okay. You just have to read those digits aloud at every call, and then you're immune. Yeah? Well, that's right. And well, yeah, well, just let me go back a little bit here. PGP phone did not use that. The PGP phone didn't actually have anything at all to do with PGP, except the name. The only reason for calling it PGP phone was to sort of capitalize on the trust that people had for PGP. The crypto was just as strong as PGP, and so I called it PGP phone. I think that after you get the secure call set up, there's nothing wrong with exchanging credentials through the secure channel. I mean, for example, if you wanted to know for sure that you were talking to, the Undersecretary of the Air Force, you could do that, but send a credential through the secure channel that you've already set up in this way. I think it's a separate problem. I think that as engineers, we tend correctly to take a large complex problem and break it into smaller, more easily solved problems. That's a good thing. But when I think about, Whitfield Diffie said that in order for two people to just want to encrypt something between them, they don't need a third party. They only need a third party if they want to do something with identity. To have their key signed by a certificate authority, for example, or a trusted introducer, as we like to say in PGP. Well, I think that I would rather rather than have the two problems of setting up a secure channel that's encrypted and setting up and knowing the identities of the two parties in some kind of highly authenticated way. I see those as two problems, and rather than take these two problems and combine them into one super problem, I would rather break them into two sub-problems and solve each one separately. That's the natural way that engineers like to break things down, And so what this does is this solves the first problem. And the second problem ought to be solved, too, for some people that need it. I mean, most of the time, you know who you're talking to because you talk to them every day. Lots of stock traders trade billions of dollars a day in stocks and securities just because they know who they're talking to on the phone on this public switch telephone network. They know how many kids the other guy has and where he vacationed and his wife's name and everything else. And he talks to him and he knows him very well and he trades $1 billion a day with him in monetary currency exchanges and things like that. Those are important transactions that entire institutions rely on. And yet no one's complained, oh my goodness, you didn't have a digitally signed certificate. Of course you don't. It's worked for years without that. But if you really want to have that, you can. But it should be sent through the secure channel as a signed credential that doesn't have anything to do with setting up the encrypted channel. That's what I think. Behind you, there was, yes? I was going to try to have something done by today. I actually I have a document, but I need to sort of beat it in shape a little bit. Oh, when am I going to have a protocol document? I've got a protocol document. I'm going to be traveling next week. When I get back, I'll work on it again, and within 2 weeks, I'll have a protocol document. I'll put it on my website.
There's a couple of questions back there.
Yeah. Yeah. That would require a lot of extra bandwidth. You want to send this all through a steganographically a steganographic conversation underneath a Muzak, right? Okay. That's kind of cool, but you know the problem with that is that this would be a standard, and you can't standardize steganography. It's standardized. You know, I remember one time a few years ago, some guy called me up and he said he came up with this idea for hiding messages in photographs, and I said yes, that's called steganography. And he said, really, it's been invented already? And I said yes. And he said, well, I wanted to make it a standard. This is sort of like having Samsonite luggage standardize all their luggage that they build to put a secret compartment in the lower left-hand corner to hide the cocaine so that the customs agents don't find it. I like steganography. I think it's really fun and cool. And maybe someday I'll write a steganography package. I've written software for a while, and I'd like to get back into it. And maybe they'll do it for that. It's just for my own amusement. But I don't see it as a serious thing that millions of people can use every day, because then people would catch on, and it wouldn't be, you can't hide the fact that there's a message if every photograph. If all the email that got sent got changed, nobody was sending email anymore of text. They were all sending photographs of Mount Rushmore, then the authorities would say, I think there is steganography going on here. Yeah.
Does your product roadmap currently include working with a hardware vendor, so it's not a software?
Yes. In fact, I actually strongly prefer using ordinary telephones. And, I think that, VoIP, VoIP is okay as a VoIP client you can put on your laptop if you're a road warrior and you want to set up in a hotel room. But I think that most people sitting at their desks prefer to use normal phones. And so, yes, it's an important thing to put it into the firmware of the desktop phone. That's why I made an effort to make this interoperate with the rest of the VoIP universe. Every SIP phone I can call. I guess I could show you calling the Free World Dial-Up Echo server,
Question over there?
Yeah. Louder? Yeah. Yes, I would like to do a conferencing solution. In order to do a conferencing solution, you have to. It's really kind of like this, but you're just calling into a conference concentrator, and you're setting up an encrypted link with each of the people from the one that's mixing all the sound together.
This guy in the front here.
Yeah.
I can't help but think about the movie It Was Sneakers, where they take people's voices and cut it up. And during this talk, you said 18 letters. You said the sounds of 18 letters, so if someone were to find the talk, they could kind of rearrange it for
You've been counting all my phonemes?
Yes.
Wow. Okay. That's a separate problem, though. Actually, what I did with PGP Phone is I didn't read letters aloud. Instead, I came up with what I called biometric words that I made 256 phonetically distinct words. And I hired a computational linguist to do this. And he went and got these massive dictionaries, and he used genetic algorithms to find the optimum set of 256 different words that had the maximum phoneme separation between them. And actually, he had to generate like 300 words because we had to throw away a lot of them because they were words that you probably don't want to have. And at the end, we had something that was a lot like the military alphabet. Instead of 26 words, there were 256 words, each one representing a byte. And so then you could just read 3 words. And the nice thing about that is that, for one thing, it's easier to understand. But another is that you can actually, if you're really, really worried about these really esoteric attacks, where they substitute somebody else's voice in or something like that, then it's not just the sound, it's also, you could weave them in to a conversation. I mean, if one of the words is ski lift, You could say, if you know the guy, you could say, well, remember the time when we went to Colorado and went skiing? Well, we used a ski lift, okay? And, that's one of the words. And, I defy the attacker to, to come up with an attack for that. He has to know everything that the two people know. So, we could use something like that for this. A lot of people who use PGP have seen this word list, and we use it for PGP fingerprints today. But it originally was started with PGP phones, so maybe it's time to bring it back. John, you wanted to say a few words. Or should I? How much time do we have? When is our time up? 10 minutes? We got 10 minutes? John, why don't you?
Okay. I've been working with Phil on this and reviewing the protocol documents, looking at test versions of the software. I think that what he's doing is really important because of the way that it takes the existing system and layers of security on top of it. The philosophy that a lot of us are using now is that there are a whole bunch of protocols that are out there. There are a whole bunch of things that we have built that if we were to redesign the entire infrastructure, we might do it differently. But we take what's out there. It's kind of like using the existing roads. If I were going to redesign the highway system, I'd probably do it differently than we do it today. But if you want to build a good car, then you have to have it run on the existing roads. So some of the advantages that this has in that it can take, for example, an existing trust infrastructure like PGP or a credentialing system and have that be part of it, excuse me, but also have the system be able to run with just two people. That was one of the key advantages of PGP in the early days, and still is, that you don't need anything more than 2 copies of PGP to start doing things. What we have been doing at PGP Corp that's similar to this is that we've been doing instant messaging that doesn't require anything more than 2 copies of PGP. And the advantage of this is that it becomes a scalable system where you reduce the friction on the network effect. If you make it so that anybody who just goes and gets this phone or a compatible one is now all of a sudden doing secure phone calls without having to do anything else, and if you don't want to be bothered with things like the identifiers, well, you have the advantage of knowing that you are talking to the handset or the endpoint that you were talking to before. It may not be the same person, it may not be any of the other things, but you know that there's this continuity of security which starts building up a completely secure system that as a network is hard for somebody to break in, and as it grows becomes even harder for it to be infiltrated.
Yeah. There is a tremendous amount of scalability by the fact that it doesn't depend on an infrastructure. And, you could have a zillion people, that's a zillion with a Z, use this, and it's not going to drag down an infrastructure. I do the key association entirely in the RTP packets. I don't even use the SIP packets. Because, in fact, you could actually replace SIP with some other mechanism, and I don't care. Once the RTP packets start flowing, my protocol kicks in. And I think that's a better way to do it. Just like the old PSTN days. You don't know what the connections, you don't know what mechanisms the public switch phone network uses to set up the connection. But once you've got it set up, you push the secure button, and you go secure. And you can unilaterally determine if it's secure with just you and the other person. Now, the other VoIP standards that talk about, there's MIKE, and there's some other things that are going on that involve public key infrastructure, or involve trusted servers, or involve sending SMIME encrypted packets in the SIP packets. Those are all very much, they're sort of institutionally driven. Designs tend to resemble the institutions that designed them. And in 1991, when PGP first came out, I made the sad mistake of not learning about what else was going on at that time. And I discovered, unfortunately, much to my embarrassment, 1 week before, 6 days before the release of PGP, I found out of the existence of an email encryption standard called PEM, Privacy Enhanced Mail. And PEM was an RFC, and there were a lot of companies behind it, and I thought for sure it was going to crush PGP. In fact, I even considered not releasing PGP. I was so discouraged because of what I saw that PEM was. But then I started taking a closer look at PEM, and I realized that it really wasn't the right approach. It was very much centrally controlled, and it was just the wrong approach. And I thought, I'm going to go ahead and release PGP anyway. Well, it turned out PEM did not crush PGP. Au contraire. And so right now, there are other approaches being considered for VoIP encryption, but I think it would be best to push ahead with mine.